Okay, thank you. So I'm Michael Cashmore. I'm a Chancellor's Fellow at the University of Strathclyde. Before that, I was at King's College London in the Human AI Teaming Group. And there, most of my research has been on integrated planning and execution, and then later on in explainable planning and planning with human collaboration. I'm also very interested in tools to enable automated planning on robotic systems. And the talk I prepared today kind of mixes all three of those kind of areas a little bit. And I want to talk about robust execution of temporal plans. Let's have a look. So this is sort of an outline of the talk, and I don't expect to go through all of it because I think the first half is going to be more interesting, and if anyone wants to interrupt me and ask questions and have a discussion, then I encourage that. But I want to start by talking about temporal constraints, so specifically plans involving time and action with duration. And then I want to extend that to numeric constraints and uncertainty that go beyond just time. And then if we have time, we can talk more about recovery procedures and plans as programs. Okay, but let's launch into temporal constraints first. So this is a sort of example plan that might be generated by an automated planner. So an automated planner could generate a series of actions. In this case, it's a temporal plan. These actions have some duration. So this is perhaps hours. And these actions are scheduled in time and can occur concurrently. So for example, I agree what the content of the seminar is. I send an abstract over. I then have to generate the slides and contents. It's probably minutes rather than hours, and deliver the seminar. And should I have been asked this in October, right after sending the abstract, an unexpected event would have happened in my life, and the execution of this plan would have failed. This is not something I could have predicted. It's not part of my model. So I have to decide what to do. Can this plan be repaired? Do I have to generate a new plan entirely from scratch? Is the goal even possible to achieve anymore? I might have to create a new goal for myself. So just to give it a little bit more of a realistic, well, that was a realistic example, but to give it a bit more of an automated systems example, this is some previous work from several years ago now on autonomous underwater vehicles, which were meant to perform inspection and maintenance of seabed facilities. The idea behind this project was for persistent autonomy. We wanted these AUVs to act for days or even weeks on the seabed facility while minimizing human intervention, because human intervention in this case was quite expensive. So we cared very much that the plans that they generated are robust and that the execution be robust. Okay, and there's a lot that goes on under the sea, right? There's a lot of uncertainty in the duration of actions depending upon the currents that are pushing these AUVs around. And if something does go wrong, like I showed you in the previous slide, and they have to replan or re-goal, the amount of time they have to do that can be very limited, because they can't stop and plan for, let's say, an hour, simply because the current's going to push them. And by the time they finish thinking, they're going to be in a completely different position, and the plan that they generated may no longer be viable. So we wanted to limit them to 10 seconds of thinking time. Okay, and I have some other example domains that we've been looking at. So most of these are from my time in King's College London, and we can discuss these maybe a bit later if you want. All right, just for those who are kind of unfamiliar with automated planning, I wanted to start with a very high level. What might an example system for planning and execution look like? It's something like this, where you have a model of your problem, and you have a state which stores the current environment that you're in. And these can be passed to a planning system, which uses this model of the capability of your system and what it can do, and the current state to generate the sequence of actions we call a plan, which will achieve the goal. Then this is going to be executed by being passed to some lower level platform, which is constantly sensing, updating the state, and it gets monitored. So we want to make sure that the plan remains valid and that these actions are succeeding and everything's going as we expect. And when it doesn't, you might have to replan. This is a very simple replanning system. And given this, we have these questions we might want to ask during execution that happen in this red box here. Is the plan still valid? Do we still want to keep executing it? Can we guarantee that it's going to remain valid? Probably not. I mean, the world is very random, but what guarantees can we have? And given those guarantees, what guarantees can't we have? Where is the plan most fragile? Where is the highest points of risk? These are obviously useful in the execution algorithm. As soon as we include human collaborators, it becomes very useful questions from the point of view of explainability as well. Okay. I'll skip this slide quickly. This is just a framework that we have for automated planning on robots. I want to make is that these circles correspond to nodes, components which are doing something in the system. But the behavior during execution isn't contained in any single component of this system. We find that what the robot ends up actually doing becomes an emergent behavior of all of these components acting together. And it's very difficult to explicitly formalize or analyze what's going to happen during execution on board an autonomous system. So what I'd like to look at now is what can we analyze just by looking at the plan? So that's second question. What guarantees can we really make about execution, about how fragile it is and how flexible it is? And in this first part of the talk, we'll look at, as I said, just from the point of view of temporal constraints. So here is an example plan. In this case, we have the first number is the time at which the action is scheduled to be dispatched. And on the right-hand side is the duration that the action is expected to take. And this is generated using a deterministic model. So we don't have any uncertainty in the duration of actions. We just chose a conservative estimate of the 80th percentile of what that action normally takes. And the robot's expected to execute this. Now, one way we represent this for execution is instead of as a list like this, we represent it as a temporal network, which looks like this. So here we have the start of the first action and the end of the first action. And a forwards arrow in this network corresponds to a constraint, AE minus AS has to be less than 40. So you have a sort of linear program that comes out of this. And this backwards arrow here with the negative, that's the lower bound. So this is more or less saying that these two actions must be exactly 40.534 seconds apart. And I might also represent that with a single arrow like this. This just means the same thing. It's just two different ways of drawing the same graph. So my whole plan might look like this, where I have my zero time, my beginning of the plan execution, the first action, which happens at time 0, the end of the first action. You can see that there is 0.1 second between the end of the first action and the start of the second one, and the second one lasts 120 seconds. This is a fixed sort of deterministic plan. And there may be a task deadline that could be represented as a constraint like this. This is quite an efficient way of graphically representing all of the temporal constraints in your problem. Now the question is it possible to execute this plan and how much flexibility remains? There are a bunch of very simple algorithms you can use to determine whether or not this is a valid plan, whether or not there's any flexibility remaining at all. As a very simple example down here, if your lower bound here and your upper bound represents some positive interval, that is your upper bound is greater than your lower bound, then there is still some time available to schedule the end of this action. Whereas if it goes the other way, your lower bound becomes greater than your upper bound, of course, your plan has failed. There's not enough time left. While that's kind of trivial for a single edge, it actually remains true over a number of different edges, and it will be represented as a negative cycle in your graph. As you can see between these two time points, if this negative value becomes greater than the positive value, you'll have a negative cycle. So simply by checking the entire graph for negative cycles of any number, of any length, you know whether or not your plan is still valid with respect to the temporal constraints. And given that, the execution algorithm is actually very simple. This is from this paper here, and it more or less says take one of your time points, which is not ordered after anything, and execute it, and then propagate those constraints, and that's it. So ignoring uncertainty for a moment, representing your plan as a temporal network means that it can be executed very easily and very efficiently. Okay, now let's bring uncertainty into it, because that's what's interesting here. So we looked at just there, what does a simple temporal network look like? Simple temporal networks have a number of extensions, which I've listed here, and I know what some of these are. But I'm going to be interested right now in talking about simple temporal networks with uncertainty. So that's STNUs. So an STNU, you might have a plan generated by your deterministic planner still that looks like this, and you want to inject the uncertainty. And in this case, what we're uncertain about is what is the duration of these actions? It's not very likely that moving the AUV from waypoint 0 to waypoint 12 is going to take exactly 40.534 seconds to the millisecond. It's going to have some uncertainty based on, what's the current doing? Are there any obstacles? So we replace for each action the lower and upper bounds for these temporal constraints with these variables that are now uncertain durations. So the length of this duration here between BS and BE is actually going to be a random time drawn from this interval here between LB and UB. And the time at which these red time points happen, at the time at which they're scheduled, is no longer controllable. It's not something I schedule and I choose to dispatch. Instead, it's something that I observe. So I would choose to begin the execution, I would choose to begin the first action, and I would have to wait between L and U until I observe the end of the first action. And this is sort of more intuitively how you'd expect it to work on a robot. You send the command, and then you have to wait for the command to say that it's completed. Okay. But now, what does a negative loop mean in this situation? What does it mean for there to be flexibility here? Just because there exists a schedule that will satisfy these points doesn't mean that schedule is likely to happen during execution. So I'm not interested in finding a solution to this STNU that is a schedule of time points. Instead, what I need is a strategy that somehow guarantees successful execution based upon these random observations. Now, a temporal network with uncertainty has 3 different properties which govern what kind of strategy I'm going to be looking for. The first, strong controllability, that's the strongest property, and it's the nicest property to have. It means that there is a single schedule for all of the controllable time points that will work no matter what happens with the uncontrollable ones. A strategy can be a schedule that is guaranteed to succeed. This is nice to have because it basically means I can close my eyes, execute my plan without making any observations, and I'm guaranteed to not violate any temporal constraints. If anyone wants to ask questions about this, I can stop and I draw an example of a schedule that's a network that's strongly controllable. Weak controllability is on the complete opposite side of the schedule. With strong controllability, I'm more or less guaranteed to succeed. Weak controllability just means that I'm not guaranteed to fail, but there's no guarantee on success at all. All it means is that for some assignment to all of the uncontrollable durations, there is something I could have done to succeed. There is some schedule that will work. Now, the trouble with weak controllability is that I don't know what that schedule is before I start executing. I might only know what schedule would have worked for this plan after I've made the final observation, and that could mean looking into the future. So while this plan is not guaranteed to fail, my strategy, there may be no strategy that guarantees success at all. And somewhere in the middle of strong and weak controllability is dynamic controllability, which is perhaps the most useful and the most common to see in a plan, which is that there is a strategy that will execute all of your time points such that all the constraints are satisfied, but I will have to make observations on the way. So for example, if I have two actions that I need to accomplish one after the other, and the second action has to be performed no more than 10 seconds after the first one. Because remember, that 10-second window is the longest I want to wait before my underwater vehicle is pushed by the current. I can't schedule them beforehand because I don't know when the first action is going to end. And if I schedule it too late, I'll miss that 10-second window. And if I schedule it too early, the first action might not have finished. So it's not strongly controllable, but it's still trivially executable. I execute the first action. As soon as I observe the first action is completed, I execute the second action within 10 seconds. It's dynamically controllable. So I can execute my time points as long as they depend upon observations in the past and not in the future. Okay, so that was a very simple network. This is the slightly more complex network with uncertainty that represents the plan. I believe there's two agents in this plan. There's a robot and there's also a human. And all of these edges represent the temporal constraints between different actions. A lot of these temporal edges are redundant and could be pruned, I think the red ones in particular. But you can see that when you put this in front of a human, they might not quite understand, what the plan is doing and how best to execute it. So first of all, having these algorithms, very simple algorithms to dispatch temporal networks and understand whether or not the plan is still valid is very useful. Second, having tools to analyze these networks and present explanations to users would be very useful. Especially, if your AUV suddenly returns to charge and you don't know why, it could be because of a temporal constraint, not now, but minutes or even hours in the future. And explaining why that temporal constraint has been violated can be quite complex. So let's take a look about how can we take this network here and go beyond just temporal uncertainty and also talk about explanations and a sort of a visual representation of the plan that the human can use. Okay. So look at beyond temporal uncertainty and at robustness envelopes. Before I move on, does anyone want to ask any questions or have any points to make about the last section? No, that's fine. I'll assume that I'm crystal clear. Okay, so let's talk about robustness envelopes. So this is the same AUV, the Girona 500, and the same plan that we saw before. As I alluded to before, this network with these red uncontrollable time points, this could be represented as a kind of linear program like this, right? And this overall constraint can be represented, as a sort of constraint like this. Now, this linear program can be graphically represented as a region in this case, two-dimensional space, right? I'm assuming that we have two uncontrollable variables here, A and B, which is the duration of action A and the duration of action B. So we have a two-dimensional space, and in that space, we can draw a region. Each point inside this region corresponds to an assignment to these two parameters, and outside the region, each point in this space corresponds to an assignment to those parameters, and the region encapsulates all of those points for which the execution would be valid, and outside the region are points for which the execution is going to fail.
Can I ask a question?
Yeah.
Why are the numbers in the linear equations in the bottom left different from the ones in the graph in the network? I thought
No reason.
Okay.
I guess to make the region look better.
Right, but normally that'd be 0 to 40.534 and 0 to 120.
So, well, typically there'd be. So in this case, we have a fixed deterministic duration on this action rather than a real upper and lower bound.
Or to be equal.
So you might say that the action is going to take between 35 to 60, for example, some conservative estimate. One of those previous graphs, it's too far to scroll up, was the PSTN, which is the probabilistic temporal network. That's a kind of extension to the STNU, where edges are represented rather than by an upper and lower bound with uniform distribution, you can represent those edges as a probability distribution over the duration it's expected to take. So as the AUV operates under there, you just record the observations as you go, updating your probability distributions and getting a better idea of how long these actions are really going to take. And then you can say, well, I want to capture 90% of that probability mass and make sure my plan is robust for that. So your valid parameter region here would actually be covering up some percentage of your probability mass, and so on. And of course, then you can try to maximize that size of that region. All right, so this is a snippet from the domain that generated this plan, and there's a plan below. We have this action do hover controlled. So this is the slow version of moving the AUV that's a bit more accurate, but a bit more slow. This is written in PDDL, which is one way in which planning problems can be written. The effect of this action is, strange enough, it's to observe the waypoint that you're moving to, move you away from the waypoint you're at and move you close to, but not at the waypoint you're going to. That's how to read this. Now, there's a lot of numbers that appear in here. Obviously, there's the duration, which in this case is just the distance divided by the speed of the vehicle. And what we were doing with the simple temporal network with uncertainty is saying that these durations are no longer a fixed value, but instead can vary. What we want to do is actually take other numeric constants in both our domain and our plan and replace them with variables that are allowed to vary. So we can change the speed of the vehicle. We can say that the actual amount of observation we managed to achieve of this target waypoint is something that's uncertain. It's based upon, how cloudy was the water, how much backscatter was there from the light. Now, although these two variables, the speed and the observation, can't appear inside our temporal network, the speed does have some effect actually on the duration of some actions, but the observation doesn't. It's completely free from the or independent from the actual duration of any action, but it does have an impact on whether or not our execution is going to be successful. We can't include it in the temporal network. We can include it in our valid parameter region. So what we want to do is find this valid parameter region for all of these. So there's 8 of them. So in 8-dimensional space, we have some 8-dimensional valid parameter region that corresponds to an assignment to all of these numbers that represents a valid execution. And we're interested in knowing, okay, well, what does this region look like? Does it even have positive volume? If it doesn't, then that means that there is no assignment to these for which my plan is going to be valid. Now, this region can be quite complex. These parameters can be dependent upon one another, but your region may also end up to be discontinuous or convex. Generating it is fairly tricky, but it is possible, especially if you're generating it offline. You can then also generate the decoupled parameter region, which I'll explain on I think in 2 slides time, so I won't go into it right now. So here's an example of a 3D parameter region. So I generate my plan, I inject all of my uncertainty into the plan, and then I generate this parameter region. Intuitively, what you might consider is that my deterministic model for which I generated my plan corresponds to a single point inside this region. And then I said, okay, well, I generated my plan, assuming that all of my observations would be exactly this, which is maybe the most likely set of observations, for example. Now, in what situations is this plan actually valid? And then you sort of expand that point to fill a region. And that region says, here are all the perturbations in the world for which that plan remains valid. And intuitively, if you make an observation that lies outside of this region at any time, your plan's going to fail. And it may not fail right now, but it's going to fail at some point in the future. Okay. So that's part of this execution monitoring. You can just pass this region with the plan to your execution, your plan execution component, and it can just check observations against this region. without having to do any costly validation of the plan. So you might make an observation. When you make an observation, let's say on this axis, you can slice the shape and say, okay, well, now we have a 2D valid parameter region that corresponds to the world we find ourselves in now. If ever that projection is zero volume, then you're, or zero area, then you're done. Okay. This observation, it could also be a choice, right? You might also be choosing when to begin an action. So I can choose, for example, on this vertical axis, when should I dispatch this? This gives us some hint of like, well, maybe I want to dispatch this action that maximizes the remaining volume of my valid parameter region. It gives you an idea of which choices maximize future flexibility. Okay, now I said I'd mentioned decoupled valid parameter regions, and this links to dynamic controllability. I have two axes remaining here, and I have to make an observation or a choice for each one of these. But the observation and choice I make for one will actually impact what's possible for the other. And if the other one is out of my control, I might want to decouple these. So I've cut off part of my region, and I've said, okay, this square here is my new valid parameter region. Any point that lies outside of that no longer corresponds to a situation in which my plan is failed, just a situation in which I'm going to consider it to have been failed. I consider it to be too risky. Because now I can make a choice inside this remaining square region for one axis, and no matter what I pick, I know it's going to have no impact on the other axis. I've decoupled these two parameters. Okay, so this is now the square is sort of like my strongly controllable plan inside the possibly weakly controllable outer region. Okay. So here we go. An envelope with a positive volume represents a weakly controllable plan, and a decoupled envelope with a positive volume, like a hyperrectangle, corresponds to a strongly controllable plan. So I can pick all of my dimensions which correspond to choices, assign something to them, and it doesn't matter what the observations are going to be because we have a hyperrectangle. Okay. And dynamic controllability really depends upon, well, what order are these choices coming in? All of my axes in this n-dimensional space are ordered. So it's a little bit more complex to talk about dynamic controllability. What's important here is that these properties, weakly controllable, strongly controllable, dynamically controllable, previously were only referred to temporal networks and how flexible is this plan with respect to the temporal constraints. What we're saying now is actually any numeric variable could be uncertain, and we want to know how controllable it is with respect to all of these. Okay. Right, now let's talk a bit about fragility and how the explainability works into this. So here again is this very simple plan with two actions. And let's say there's some constraint on this second action B that says, well, actually, this plan, maybe this is a fragment of a much larger plan, and that plan is only going to be valid if this action B takes something between 119 and 120 minutes. That's very unlikely to happen with an AUV. It's probably going to be much more uncertain than that. Just to bring it back to what I was saying to Bob about this probability distribution, maybe that captures only like 2% of my actual probability distribution for that action. So I'm saying, well, 2% of the time I'm okay, 98% of the time this plan is going to fail. That's an immediate way to say this plan is very fragile. It's a very risky plan. And what that would look like in my valid parameter region is a very thin area of my region, an area where it looks very brittle. It could be in a single axis, in which case that's very easy to explain to a user, right? If it's like this, I can say, well, here's one action that has to be accurate within 1 minute or we're going to fail. That's a nice way to explain something. It's very straightforward, but it might be a little bit more complex where actually both of these actions have quite a large an interval in which they can be achieved. But the actual region is still very fragile because of the interaction between these two actions. And in this case, just looking at the region, you can see that it's very thin. You can see that there's a lot of, there's not very many points for which this plan is going to succeed, depending on what the uncertainty of these actions are. If both of these are observations, then you can tell that you're probably going to fail. Now, as soon as, for example, I make an observation, okay, action B took this amount of time, now I can see on action A that the interval has shrunk a great deal, and this probably captures a very small amount of the probability. But it would be nice to be able to explain to the user where is the fragility in the plan and how risky is it before we actually make any observations. And it may not be fragile right now, it might be sometime far in the future that is our most likely point of failure. And if we point that out, then we can do something about it in advance, which is the second half of this talk. Okay. And so, you might have a human operator who's looking at a screen with all these shapes, and I'm not an expert at all in human-computer interfaces, so I don't know what form this should take, but this is the sort of analysis that should be feeding into the interface that a human operator or collaborator would be using with a robot. Whether it's graphical like this or something like natural language, the robot should be able to express quite concisely and clearly what kind of interaction between actions is causing the plan to be fragile, and when, and what can be done about it, rather than dumping that huge temporal graph in front of a user and saying this is the plan, or a list of actions, even worse. Okay, or a Gantt chart, which, although it shows you when the actions are, doesn't show you what the real constraints between those actions are. Okay.
Michael, can I ask a question?
Yeah.
Do you always assume that you'll be able to represent this fragility analysis in 2 or 3 dimensions? And if it's more than 2 or 3 dimensions, how even to visualize this?
It's a good question. So I expect not. I think 2 and 3 dimensions is basically only good to put on slides to explain what's happening. But when it comes to a real plan, there's going to be too many variables. There's going to be many more variables than 2 or 3, I should say. It's not too many.
Yeah, and then how to make sure that it's still, whatever model you get still has some explanatory power and to the human.
So my hope would be that there is a way to, let's say these are 2 dimensions of actually a much larger sort of n-dimensional region, but the actual fragility is not going to be a component. So it's not going to be a product of all of your dimensions. Perhaps there's only 1 or 2 factors which cause this risk. Mm-hmm. Now, if it is the case that every single action somehow contributes to this risk, then it's much more difficult to explain in this way. But if you can extract just 1 or 2 or 3 dimensions and say, okay, well, these are the contributing factors to the lack of flexibility in this plan, for instance, then you have something to work with.
Okay.
I don't think that's too strong an assumption, right? If somebody asked me, well, why is such and such going to fail? Why might you miss the talk? I might say, well, the train arrives at this time. I have this thing to do before I get to the train, and it takes me this long to get to the train. Okay, that's 3 things, and already my explanation is, as a human, is getting quite large. But I might even get rid of one of those axes and say, the train arrives at this time, and I might arrive at the train station between these 2 time points. So immediately you understand that there's this one event that has a very, very thin area of my robustness region. Does that make sense?
Yeah, it's just something similar pops up when we discuss neural networks, for example. It's one thing if you could say there are only 3 pixels in that picture that contribute to classification, then you could easily reason. But if there are several thousands, then the trouble starts.
Yeah.
So, but yes, there are definitely situations when the number of parameters is small, and it is useful to be able to explain them like that. So
if I go back to this graph here, with the neural network, you know, you've got your fully connected layer, so everything kind of depends on everything else. And it's very hard to just pull out one node and say what's the effect of this node. Whereas in this graph, although there's many edges, I mentioned that many of them are redundant. And if I consider a single node, let's say, I don't know if you can see my mouse, I hope so. Yes. This node here, it's actually part of a causal chain which comes from the start. And I could start by saying, well, maybe only this causal chain is important. And even then, perhaps I don't need to consider the whole chain. Perhaps I only need to consider the neighbors of this node. And the actual explanation I can give is just a part of these two constraints here.
Yes, okay. It is more interpretable than neural net, for sure. Yeah. Thank you.
Okay. So, is there any other questions, or anyone want to discuss stuff if I move on to the sort of recovery procedures? Okay, I'll move on to the next section. So in this section, I want to talk about, I guess, a different kind of uncertainty, which is a more discrete uncertainty. It's not that some number is going to take its value from a region that I'm quite confident represents that uncertain number, but instead some kind of discrete failure where an action might fail, or you know, a baby might appear. If I know in advance, well, let's say one of these things happens, what can I do? The first option is what I showed you in that very simple execution loop at the beginning, which is when the plan fails, I can try to replan from failure. I stop, I have 10 seconds to replan, I generate a new plan, and I execute it. I might be clever and I generate my new plan while I'm still executing, as long as I'm confident that I'm not taking myself into danger. If you're a bit more clever, you could try to replan before failure. If I know where the plan is most fragile, or I know what are the most likely actions to fail, I can, while I'm still executing the plan, I can say, well, in about 1 hour from now, I have an action that's very likely to fail, or I have that time limit that's very narrow. Let's assume I'm late. If I'm late, what am I going to do? If I miss the train, how am I going to get to work? And you can, as you're executing, replan before failure and generate a contingent plan. You can add a branch to this plan, so that in the case of that failure, you can divert execution elsewhere, and you're still on board to succeed. But if you're even more clever, perhaps you can plan recovery procedures. And the difference here is that when I'm replanning before failure, I'm saying that I have a plan that I'm executing. I know when that plan is likely to fail, and I can do something about it. Now what I'm saying is that I haven't got a plan yet. Maybe I don't even have a goal. I have my model, but I know based on my model which actions are most likely to fail. I know my goals are going to be some kind of inspection and valve turning goals, right? I'm a robot that does seabed inspection and maintenance. There are these templates for recovery that are always going to appear in my replanning attempts. You know, if I get pushed off course, I'm always just going to replan to move back on course as long as some time limit is not breached. So why not plan these recovery procedures in advance, and then when I generate my plan initially, rather than start replanning from failure and analyzing fragility, just combine that plan with these recovery procedures to create a more complex plan that includes some branches and perhaps loops that will automatically repair these things without me having to do any extra brain work. Okay, so for example, if I'm an AUV for seabed inspection and maintenance, I might lose my localization and forget exactly where I am in the map. My battery might be draining faster than expected. I might be moving to a panel to turn a valve. I get there and I can't see the panel. I can try to turn a valve and not be correctly turned, all these sorts of things. And what I need to do in the case of these is usually the same sort of thing. If my battery is draining faster than expected, and the plan's going to fail as a result, I need to return to the charging station. There really is no other option, or I'm going to lose the AUV. There's no reason to replan to do that. Even before it happens, there's no reason to replan. I know what I need to do. I need to return. So this is some work from Luca Iocchi and Zappara, and the names down at the bottom of the screen there, on representing your plans as Petri nets. So these Petri nets look quite similar to the simple temporal networks we saw at the start, where we have these places that represent the initial place. The start of the action takes you to the executing place, and then the end of the action takes you to the output place. And you'll move a marker along this as you do in Petri nets. And you move the marker when you decide to execute an action or you make an observation, much like scheduling time points in the temporal network. So what's nice about these Petri nets is now you can start adding branches directly into them and say, well, my action has two possibilities here. I observe that the action succeeds, or maybe I observe that the action fails and I move to this other place. So you can plan short contingencies. You can do this online, but you can also plan these short contingencies as recovery procedures and represent your actions as these little kind of state machines that will make your plan that you generated from the planner much more complex during execution. So in their work, they represent these execution rules in this sort of form. These are written by hand by a user, where they say, okay, well, here is the condition. If this condition is met during this place, so while I'm executing this action, if my battery level falls below this amount, this rule is met. Then I should do this value here, which is a subplan that's represented as a Petri net, and then I should do one of these things: report failure. So I should return to recharge the AUV and report failure and ask for human intervention, for example. And then you take this execution rule, it gets compiled into these sort of, you represent your plan as a whole Petri net, and you compile the execution rules into it. So your plan sort of explodes and becomes much more complex and much more robust at the same time. Okay. What's missing here is temporal planning. It doesn't include the time and numbers aspect, but I assume that's something they're working on. Okay. So I want to just talk now about what might you do in case of this discrete uncertainty. How can you possibly replan, how can you possibly include these recovery procedures into a plan that includes time and numbers, and most importantly, concurrent activity? So here's a quick example of an action that has some duration, for which what you do to replan really depends upon the kind of duration we're talking about. So we've got this durative action that says, as a precondition, I have to be at A. As the effect, I'm no longer at A. I guess that's a strange not sign. And I'm at B. And the duration takes between d min and d max. Okay. So I move from A to B. It takes this amount of time. Stay simple. But this description here actually corresponds to two different, very different kind of executions. In the first, driving, I'm driving from A to B, and if something goes wrong, if some execution rule is met, or I notice using my robustness envelope that the plan has failed, and I'm halfway from A to B, I can do something about it. I can stop, I can replan in that position, I can go back to the start, I can decide to continue on to the end, I could divert and go to C instead. The other kind of action is a ballistic launch. I launch myself in a catapult, and I'm sailing through the air, and halfway to B, I say, oh no, this plan has failed. I really don't have many options there. I have to continue towards B. I can't divert to C unless I'm Superman. So we say that the ballistic launch is non-interruptible, whereas the driving action is interruptible. And this really comes into play when we start thinking about, that first of all, that second layer, where I want to replan for future failures, or I want to replan during a failure, but I want to do so concurrently with execution. it really matters what is currently executing at that time. Remember in that first slide, I showed you that there's this state which stores the current environment. That's going to be the initial state from which we plan. If I have non-interruptible actions that are currently executing, or the environment is dynamically changing, then I have to plan from a state that's continuously changing. And there's a few ways you might want to do this. So one thing you might do is say, well, let's think ahead to when everything that's currently going on is going to finish and plan from that state. If you do that, it might work, but you also might be continuing driving to B. And once you arrive at B, you realize that actually the new plan is best if you started from A. So the very first action is to drive back to A. So in some cases, you may be ending up making more work for yourself. In the worst case, the plan failed because the battery was too low. You continued the execution of an action that you shouldn't have, and now you've moved yourself into a dead end, and the AUV is going to be unrecoverable. So the idea of planning for some future state, well, nice, is not always the best thing to do. Secondly, you might be able to divert this execution. So I mentioned before that, we just stopped the AUV and we gave it 10 seconds to replan. Sometimes stopping is the worst thing to do as well. So in this case, my battery runs out, I stop, I replan, and then I decide that actually I should continue to my charging station at B or go to C. But because I stopped and I waited for so long to replan, my battery continuously draining, I've actually worked myself into a different dead end. So waiting is no good, continuing execution is no good. What I want to be able to do is to divert from the current execution at any moment when it's best to do so. And that's what these two papers here are about. So Andrew Coles has written a planner which is able to plan from an initial state that's continuously updating. And the way this is done is inside the planner where it's building the plan, it builds it as a temporal network, the time points of which are relative to that 0 point, the start of plan execution. And that 0 point is continuously updated. So you're building a search tree of partial temporal networks, and these parts of these search tree are decaying and dropping off as they become invalid. As soon as a negative cycle is found, it's like, well, this solution was no good. When you find a solution, you can execute it immediately, or you can keep planning until there's a moment at which the planner will tell you, all right, the best solution I found so far, you have to execute it now or lose it. And that's what this example here is showing. There's this vehicle driving from A to B, and there's some plan that it's generating that moves you to C, and the actual cost of the action is changing as the vehicle moves, and that's all occurring inside the planner. Okay, well, I mentioned that this ties very much with the uncertainty and what sort of guarantees can you make, and how can you describe these execution rules. So I want to give an example here of the same simple executor, but it's distributed. Actually, we have two concurrent plan execution systems, and one of them is sending commands to the other as if it were one part of the platform. And that one is sending perceptions, it's sending observations back to the one on the left. So as far as the one on the left is concerned, it's the brain, and it just is dealing with this lower level platform. And as far as the one on the right is concerned, it's the brain, it's executing something, but it's receiving goals from above, as they both are. So in this case, they have some state space which is shared. I'm assuming that there's some hierarchical operation here. So the one on the right, its state space might be a more refined version of the state space of the one on the left. Its actions might be breaking down the one on the left's more abstract actions. That's not necessarily the case. You can also have two actors acting in the same environment with different models that describe the same thing, but aren't necessarily, one more abstract than the other. They just have an overlapping state space. Okay, this is just the ROS plan version of what I just showed you. So assuming that the plan that's being executed has been failed, it's executing this plan, and it sees that the region has become too fragile, and in some axes the interval goes to 0, the volume of the shape goes to 0, and the plan fails. The executor is going to want to replan, and it's probably going to want to replan online. And the reason it has to do that is it has to consider that now it's not just the sole actor in this world that's unchanging except for its own actions. In fact, the rest of the world is still changing because there are other actors in there. And it's the constraints that it must meet aren't only the constraints of its own plan, which are now failed, but there are invariant constraints for other actors that it's supposed to be upholding. So I don't know if I have a good example for that, but you can imagine that if I were collaborating in a team with other agents, I have some task that I'm supposed to do, some goal that I'm supposed to meet. That doesn't change if I've just failed my plan. So when I replan, I have to consider that the deadline for that hasn't changed. Or if I'm holding the door open for someone to go through, and I realize that, oh, I'm going to be late for my train, I can't drop that door as the person's halfway through and run to the train station. I've got to consider that I have to keep holding that door open until some other constraint is met. If I'm able to observe that person, then I can do so in a kind of dynamically controllable strategy. I can plan to wait until they're through and then run to the train. If I can't observe that person, that is, the fact that they're finished is not a percept that's passed to me, I'm in a situation with limited communication, then it's a much more complex problem. Unfortunately, I have no solution for that problem to present to you today. I'm just at this point explaining the problem space. Okay, so these are the two papers I mentioned before, which deal with planning from a dynamic initial state. This is the first step towards that kind of system, which will allow you to plan from an initial state that's constantly changing and generate plans which are then into which you can understand that uncertainty over what's changing. But these questions I have here, which invariance must the system maintain, are not problems that we've yet solved. Okay. The first, as I mentioned, the first step towards this is being able to represent your plans in such a way that provides guarantees about its behavior, specifically what is going to happen in the case of failure. And, oh, I'm running out of time. Sorry, someone pushed the chat there. What's going to happen in case of failure, and where is this plan most fragile? So just going back to my door example, if I'm the person going through the door and I know that someone else is holding it open for me, I might want to consider, if their plan is going to fail, what are they going to do to fix it? Because that's going to impact what I do. I might decide, let's not go through that door slowly and controlled. Let's rush through that door, because if they miss their train, they're going to drop it as early as they can, and they can't see me. That's why it's so important to be able to plan these recovery procedures offline, to be able to inject them into the plan later, so that when we share our plans before we go into things and execution begins and communication is limited, because maybe there is no communication, or maybe just not enough time to explain something to a human, I'm going to want to know what you're going to do when things go wrong, so that I can react appropriately. And that goes both ways, to the human and to the robot. Okay. So bringing it all together, we've got this sort of team here. This is like a ground robot with a charging station. This is like a drone which charges off it. So this is the boss, and he says, here's the plan I want you to do. But he actually says, here's the plan I want you to do, represented as maybe a Petri net, maybe as a finite state machine, or maybe as a program, an SQL program, for example. And here is the way I need you to recover from various things that's safe, given the context of the larger mission that you don't know about. And here's the robustness envelope that I need you to adhere to. It might not correspond exactly with the plan I gave you, but actually there's other constraints which you don't know about, deadlines that I need you to meet. And then the robot says, rather than, okay, I've succeeded these actions, it can say, okay, here's how I'm doing. Here's the observations I've made, and that I'm slicing away this, this robustness envelope. Just by changing the way in which we're representing the plan and representing the observations during execution, we're now able to do much more complex reasoning on board both of these machines and start to try and solve these problems. How to place guarantees on the execution. Okay, and this is just a summary, but that's the end of the talk now. If you have any questions at all about that latter half, let me know. And otherwise, I think I've used up all my time.
Let me just switch on. Thanks a lot, Michael. That was a great talk. Huge inspiration for all of us. I think maybe we should just arrange, we have Isaac Breakfast's project meetings on Thursday mornings where we discuss possible collaborations. So maybe we should invite Head at What Planning team and you and just discuss at some point. Because what we're trying to do with an Isaac grant is to build some kind of interface for AI specialists to be able to access different tools like planning tools, but also maybe neural nets. So it would be good to discuss that. And let me stop recording, by the way, and I'll give everyone a chance to ask questions. And that's recording stop.